All right. So number two, using the picture seen to the right and rounding to the nearest tenth of a meter, find the height of the tree. All right. So just looking at the picture, the height would be this distance here, which is, oh, sorry, this distance here, because that's where the tree is rooted. And that, I tried to get it to the topmost part of it. Right. So we're looking for this distance, but I'm going to do what I did last time and pull out the triangle just so we don't have all the trimmings around it. Tree trimmings. I'm going to label it up A, B, C. Oops, that was unintentional. I just wanted to move the A. All right, so I'm going to put a 23-degree angle here. They told us this one is 110, and we have 120 meters. All right, and again, we're looking for this side here. All right, so that side is side A. That's the one that we care about. I'll put the question mark over here. Let me do that a different color so it stands out a little bit. Not the nicest, but we'll just do a little question mark there. Now maybe I'll use a little highlighter, just kind of accentuate it. This side here is what we're looking for. All right. So one of the challenges in figuring out these kind of problems, they're not right triangles, so you can't just use SOHCAHTOA, can't just use Pythagorean theorem. You have to use either the law of sines or cosines. And I mentioned last time that if you have two or more angles, you're going to want to use the law of sines. If you have one or more angle, you can use the law of sines, but it might be easier to use the law of cosines. Right. So if I have two angles, and bear in mind, if I know two angles in a triangle, I actually know three of them. The last one's indirect. Okay, so I do a quick 180 minus the 110 that we know and the 23 that we know. And that gives me 47 degrees for that remaining side. Oops, don't need the thick marker. So 47 degrees for the remaining, I think I said side, I meant angle. All right. So what I want to do here is use some variation of the law of sines that incorporates A. All right. Remember, law of sines serves as a pretty good review too. We have sine of A over A is equal to sine of B over B is equal to sine of C over C. All right. So I'm going to use the relevant pair of ratios. One that I want to incorporate definitely is the sine of A over A because it has the letter A in it. Right. Now, if I have a side angle combo, like if I know the side and the angle and the angle opposite that side or the side opposite the angle, I want to incorporate that too, right? Because that's a known ratio, right? So I'm going to use sine of C over C because I know angle C and I know side C, right? So by using this setup, so we get rid of the sine of B over B, you can do a strike through if you want, it doesn't make a difference. I can now isolate it down so I only have one variable, right? So sine of angle A is, I'll use a highlighter, 23 degrees. Side A is unknown. Angle C is 47 degrees, so sine of 47. Side C is 120. The units are meters. I'm not going to, when it comes to testing, I'm not going to try to trick you with units, but like in another class, you never know, it might happen. Right? So just be careful. The question in this case is asking for an answer in meters, and it's giving us all the lengths in meters, or at least the one that we know. So we don't have to worry about any unit conversions, but that's kind of like the typical trick that teachers like to use just to kind of mess people up, especially in the physics class. Units are so important. All right.
Professor, why did you cross out scene B?
Because it's not relevant. We don't need that piece. So I'm just grabbing these two parts of the law of sines and ignoring the other part. Right. And that's
And
because I'm interested in side A. So I definitely want this ratio. And I know everything about sine, angle C and side C. Okay. So I want to incorporate this one because it's got useful information. Okay. So it's not really the case that you need to write all three just to cross one out. It's more like just decide on which two of the three are most useful. And you know what? If you get
okay.
yeah,
Yeah,
and
I got it. Okay.
cool. Yeah,
Thank
and
you.
also just to add on to that, if you accidentally select the wrong pair, you'll find out pretty quickly. So then you'd say, okay, well, let me try a different pair. All right. So in this case, remember, we could swap diagonals, right? So I can bring the sine of 23 down here. I can also group diagonals. I can swap and I can group. In this case, I want to just, or at least the sine of 23, I'm going to, oh, actually, sorry, I'm going the wrong way. I want A to be on the top of a fraction. So I'm going to swap these two. Put a little double-sided arrow there. Their positions are going to change. But then I want to take, let me get a different color. This orange doesn't really stand out very well. This 120 and send it up to the numerator of the other fraction. So I'm going to get 120 sine times sine of 23 degrees over the sine of 47 degrees, right, equals A is the only thing that remains on the right-hand side. That 120 was actually multiply. I mean, the operation is multiplication. So that 120 canceled to a 1. So you could write it as A over 1 if you want. But ultimately, it's just going to become A equals whatever this ratio simplifies down to. All right. My calculator's in radian mode. So I want to make sure I change that. All right. So go on down to settings, angle measure. We want that degrees. All right. So angle measure degrees. Then I go back into my calculation and I type in 120 sine of 23. Oops, the sign didn't take. Sine of 23 divided by sine of 47. All right. I tend to overdo it with parentheses because what happens is sometimes, especially, well, I think only with sums and differences, when I try to make a fraction out of an expression, sometimes it just puts the denominator under one term. Actually, all the time, if you don't put parentheses here, there are two factors, so it doesn't make a difference. But I tend to err on the side of caution there. I just want the 120 sine of 23 to be on the top and sine of 47 on the bottom. And so we get, they said nearest 10th, so 64.1 meters. All right, that would be the height of the tree. Now we're kind of taking liberties with this term height, because when you talk about heights, altitudes, whatever, it's usually the distance away from the ground, right? But that's in the instance where the ground is horizontal, right? Because this ground isn't horizontal, we're still looking for the height, but it's going to create an angle other than 90 degrees, right? So we're really actually looking for the straight up and down height. So my diagram's a little out of whack. When we talk about a height mathematically, if we assume that there is a ground level, that's horizontal, then it should be like you're dropping an altitude straight from the top to the ground. That would create a right angle if the ground were down here. All right. So that's we'll call it the usual ground. Right. But the ground is now up here. So it would cut off at this point, and that's where that 110-degree angle comes from. Right. So my diagram's a little kooky, but I can even move it over a little bit so it lines up a little bit more. But yeah, that's essentially the idea, that there is some horizontal ground out there, and we're trying to figure out relative to the correct ground, the contextual ground, the ground that the tree is rooted in, where, what that height would be off of that. And so that ends up being this distance here. And that's what we were looking for. All right. So going from this location, this ground, up to this height. All right. More explanation than you probably needed, but I do like to get the physics involved in it a little bit. It's not a physics course, so we don't have to go too crazy, but just to kind of not hand wave it away. So again, I'll call this the usual ground. This is up here, the new ground. All right. And that's one of the reasons why we have to use law of sines and cosines, because we're not always going to be working with a ground being horizontal and a wall, for example, being vertical, right? Making that perfect 90-degree angle. Doesn't always play out that way, right? I mean, it should if you have good construction, but you never know, right? So if you have a retaining wall at the edge of a hill, and you want to cut that hill off to put that wall up, that wall itself is going to be perpendicular with what the ground should be, but it's not going to be perpendicular with the land that it's holding back. Right. So yeah. Number 3, a derrick at the edge of a dock has an arm 20 meters long. So regardless of what, if you know anything about docks or derricks, I honestly didn't until I saw this problem for the first time, and I was like, all right, I guess that's what it is. Has an arm of 25 meters. So even though they said the derrick has an arm, you're like, oh, what are you talking about? They labeled the 25 meters right here, so you can kind of figure that out. Makes a 122-degree angle with the floor of the dock. So that must be this. That's the floor. The arms to be braced with a cable 40 meters long. So this must be the cable. From the edge, from the end of the arm back to the dock. Right, so it's supporting it. The nearest 1/10 of a meter, how far from the edge of the dock will the cable be fastened? All right, so it's asking for this distance here. We don't know what that is. All right, but I'm going to do what I did for the last couple of problems. I'm just going to draw a quick triangle overlay. Hopefully it settles into the right, generally the right shape. It does. Then I pull it out of the picture. I mean, if you have a tablet with a stylus or some other interactive pencil, that's easy enough to do. Otherwise, you're just going to kind of ballpark estimate what the triangle would look like, then label it up ABC. All right, so we have the 40, the 25, we have a 122-degree angle here. All right, now they're asking us for this side. Well, it's going to be called C because it's opposite angle C. But if I label the triangle differently, it might be a different letter. But I always like to start, just for consistency, start in the lower left-hand corner of the triangle. And it's not always like the leftmost part of it, but the one that you would call the lower left corner, and then work my way around counterclockwise. Regardless of what you do, just be consistent. Right? It develops or allows you to develop a little bit more awareness of the relationships. Right. So I want to figure that out, but I don't know the angle opposite it. Right. In order for a law of sines to work, I need to know the angle opposite a particular side. Right. Otherwise, I end up spinning my wheels like that one problem we did where we didn't end up with a solution. All right, so I need to figure out angle C. I have two or more sides. Two or more sides is an indicator that you should be using the law of cosines. All right, so law of cosines, where I need to know the angle C. So I want the C variation of the law of cosines. I'm trying to think of a good place to write this. I'll do it down here. So C squared is equal to A squared plus B squared minus 2AB times cosine of C. All right, so that's the C variation of the law of cosines. And really, a lot of this stuff boils down to, and I mentioned this last time, and I mentioned it earlier tonight, what formula fits the most stuff. All right, you have some information, which formula is going to fit the most of it. All right. The issue that we run into here is that I'm going to have more than one variable. So I would like to be able to use this to solve for angle C or side C, but I don't know either of these. So it looks like I may have to, kind of adjust and choose a variation of the law of cosines that is going to solve for something that maybe I'm not interested in solving for. All right. So if I use, and I'll actually just kind of walk you through all three of them. So the B squared, A squared plus C squared, it's good to review it anyway, 2AC cosine B. Okay, and then A squared is equal to B squared plus C squared minus 2 BC times cosine A. All right, so I'm going to highlight the things that we know in each formula, and the one that has only one variable left over to be solved for is the one we would go with. All right, so I don't know C, so I definitely don't know C squared. I do know side A and side B. All right, but I have two unknowns in this formula. The second one, I know side B. I know side A. I don't know side C. But I do know angle B. No, I don't. All right, so there's a lot of unknown here. Then the last one, I know A, side A and angle A. I know side B. I don't know side C. But that's the only thing I don't know in this formula. All right, so here, this one's going to be our winner, because even though the C is represented twice, it's still something that I know, like I can figure it out. All right. There's also another, you could use the law of sines for this. Even if you remember, I said, if you have at least one angle, you could use the law of sines, but you're probably better off with the law of cosines. It's the same idea the other way around. If you have at least two sides, you could try to use the law of sines. It just won't always work, like that one problem that we did. The one that worked and the one that was kind of a pain. All right. So if we go down this road, we'll be able to solve for side C without ever having to figure out angle C, which is kind of nice. All right. So I'm going to start making some substitutions. Side A is 40, so 40 squared is equal to B is 25 squared plus C squared is our unknown. I think I'm going a little too in the way here of the question mark, so we move that. Minus 2 times B, so B is 25 times still C is unknown, times the cosine of angle A. Cosine of angle A is cosine of 122 degrees. All right. So focusing on this, I can clean it up, but I have a power of 2 in there. That power of 2 is going to make it quadratic. So I'll have to use the quadratic technique to find the solution here. And this is where, and we did this with trig equations in the last unit. This is where algebra and trig kind of come together. All right. But I'm going to clean some things up. In a quadratic, when I solve those, I want to have everything over to the same side. So I'm going to subtract off the 40 squared. All right, so I'll just do that quickly here. 25 squared minus 40 squared. That's negative 975, so it cancels over here. to 0, negative 975 plus c squared. Now, this over here, let me get my highlighter. You know what here is? Get a lighter color. All of this is one term, right? Because it's all connected through multiplication. So I could run through and crunch that real quick. Okay, so negative 2 times 25 times, ignore the c because that's a variable, right? So times the cosine of 122. And that's going to give me, and you can write it either way. If you want to use the decimal form, then you want to round it at least 3 significant digits. So 3 decimal places, not including any zeros that might be there. Or you could just leave it as 50 cosine 58, which is a little nicer because it's exact. And even though it's a little bit more to write, an exact value is always preferred over an approximation. Right. So this would become plus 50 cosine 58 C. Right. And if I rearrange here, you'll see the quadratic relationship, and that is 0 equals c squared plus 50 cosine 58.
Professor?
Yeah.
Why does it become plus?
Oh, it's just what the calculator told me. So I put in the negative 2 times 25 times cosine 122, and it spat back a positive number, 50 cosine 58, or 26.496. And so it wasn't like we just ditched the negative. It became positive through this calculation here.
Oh, I see. I was looking at numworks. Okay, so I see you just copy whatever numworks gave you.
Exactly.
Okay, thank you.
All right, so I have c squared plus this number minus 975. Now it's up to you, but you may not want to do this using, well, definitely not completing the square. If you're talking about solving a quadratic, your choices are factoring. This doesn't look factorable. I'd be shocked if it was. It isn't, right? And I know it's not because in the directions, they say to the nearest tenth of a meter, which implies rounding, right? So they're calling for a numerical approach here. So that implies that factoring wouldn't be a logical choice. You could do completing the square. Again, don't recommend that. You could use quadratic formula, or you could use the solve function or the equation function in numworks. All right, and so that's my recommendation for a variety of reasons, but basically detailing all the pitfalls that you'd run into with all the other approaches, it kind of makes this one the most appropriate. Also, just bearing in mind, again, I've said this a few times, it's not an algebra course. So, there's no I don't want to say no expectation that you do algebra because we have done algebra, but it's not the primary focus of the course. All right. So things like this, we could just use the equation app for. And if I have I'll look at the clock after I do this. If I got a couple minutes, I'll take you through the quadratic formula approach also. All right. But in the equation app, so again, you're in your home screen, you go to equations, add equation. You can hit empty and start typing 0, shift pi for the equal sign. You could use C if you want. Honestly, I've never tried it using some letter other than the variables like the x, n, t, or theta. So I would just go with x squared plus 50 cosine 58, close them up, close it up one too many times apparently, throw an x there instead of the c, and then minus 975. All right, so just typing it in almost the way I see it. It's a little different, but I got the extra parentheses involved or around the 58, but essentially it's the same thing. All right, so okay. Then we go solve the equation. And it gives you the two answers, which is nice. For quadratics, it tends not to have a problem because it knows quadratic equations can be technically infinite. But you look at this and you say, oh, what did I just get myself into? Why would I do this? This is an awful looking answer. But if you scroll to the right, you get the decimal approximation. Now that first one is no good, right? The C value here is the length of a side in the triangle, right? So that negative value doesn't really help. With quadratics, you could get one negative and one positive answer. Right? If that happens, you go with the positive. Sometimes they're both positive, and then you have to make a reasoned choice based off of the context of the situation. Like if I got something like my first answer was 1.28, and my second answer is the 20.67, based on the context, I'm going to say, yeah, I think this distance looks like it's a little bit more than 1.5 meters. So I'm going to go with the larger one. But if they're both negative, then you're looking at something that doesn't have a solution. Right. In those cases, it's either I made a typo, not inconceivable, but more likely it's that you made a mistake in the computation somewhere. Right. So 20 point, they said nearest 10th. So 20.7 meters is what we would get for the value of X. All right. And like I said, I'll just do it real quick. No, not too quick, but I'll do it using the quadratic formula. Just so you can see, it's not one of those things where it's like a deal breaker if you don't want to use a calculator approach, which I guess is a good thing. But you know, in some cases, it's like, especially during a test, why did I not pay attention to the calculator approach? I've got like a page of work here. This is a kind of example where it could go either way. It's not a whole heck of a lot of work with the quadratic formula, and it's definitely not that much work with the calculator method. Regardless, you do still have to get to this point. Right, this is a key step in the process. I'll use a highlighter. I've used every color in creation here. I'm get a little powder blue involved for those keeping score at home. So you still got to get to this step. But then what we would do is use the quadratic formula, QF for quadratic formula. And, you know, ordinarily it's X equals negative B plus or minus all that stuff. My variable here is C. So I'm going to say C equals negative B plus or minus the square root of B squared minus 4AC all over 2A. And then I put in my coefficients. Some of them aren't that pretty, but they'll get in there. All right. So the leading coefficient is 1, so that's my A value. That 50 cosine 58, that's my B value. And we have this little conflict here where I'm saying C for the actual side C. And then I have C that represents this independent variable here. So that could be a little weird. So maybe you do want to go with X, or you could use subscripts. It really doesn't matter. I'm just going to make a note that this is side C. All right. So negative 50 cosine 58 degrees plus or minus. I get a little lazy with the degree sign. It's not the end of the world if you don't write the degree sign symbol, as long as you're aware, you know, and you set up and carry out every process correctly. And it's the 50 cosine 58 squared minus 4 times A times C, which is negative 975. I'll never learn and never make the radical bar long enough, and I always have to extend it. So old habit. Even when I was back when I was teaching with chalkboard, I would still always like cut the radical too short. I don't know. 2 times 1. So then we look at this as two separate operations. We have the minus and we have the plus. So in my home screen, I go to calculate. I'm going to make this ginormous fraction on my numworks, but I'm only going to use the minus one first, then I'll use the plus one. All right. So again, I tend to go nuts with the parentheses. So negative 50 cosine 58 minus, doing the minus one first, parentheses 50 cosine 58. Close it up for the argument, close it up for the expression. They added one in there. We want the power of 2 right here. Minus 4 times 1. So you could ignore the 1. I'll put it in anyway, though. Times negative 975. Then I'm going to close up for the top, divided by 2. All right, 2 times 1. I'll write the times 1. All right, so negative, the b value itself is positive, so I just made it negative because the quadratic formula calls for that. Negative 50 cosine 58. That's my negative b. Plus or minus, I'm starting with the minus. The square root of b squared, the b is 50 cosine 58 squared, minus 4 times a times c, so minus 4 times 1 times negative 975, all over 2a, so 2 times 1. So I hit OK. It gives me the bad answer. Go back in, change the minus to a plus. Again, it was plus or minus. I did the minus first, now I'm doing the plus, and we get the 20.67, which would round to 20.7 that we got from the calculator. So, I mean, in terms of actual work, it's really just one additional line of writing, but a little bit more with the computation. So you can just kind of go with that. And the other option would be to do it with the law of sines, but I feel like I beat this problem to death. So maybe next class I'll come back and revisit this. I'll put a star on it, and then wonder why next week that I put a star on it. I have no idea. I have no idea what I ate for dinner last night. I'm not going to remember tonight, but yeah, I figure we'll move on. Talk about vectors. In a lot of ways, vectors is kind of going back to square one. And, you know, sometimes that's a good thing, you know, like concepts that you've explored in the past that you haven't really touched in a while. You know, that's what vectors talk about. Yeah, why not? Vector. Vector is the first word of the day. Vector, as in vectors in the plane. As in to learn the properties and behavior of vectors. Vector. Trying to remember the Despicable Me quote. It was like, let's see, vector. Well, intro. Despicable Me. More. Oh yeah, vector. It's a mathematical term. A quantity represented by an arrow with both direction and magnitude. Vector, that's me because I'm committing crimes with both direction and magnitude. Oh yeah. So yeah, it's my little Despicable Me moment. Awesome movie. Underrated franchise. Anyway, so vectors in the plane. So what plane? The plane. All right, so that's like, okay, well, what is the plane? The plane is the plane that you've always been working with. All right, so it's the XY coordinate axes. And so you've always been working in the plane. Now it's a question of, okay, if it's the plane, are there any other planes? And the answer to that is yes, but that's a different story for a different day. All right, so we have a vector in the plane, that goes from 0.11 to 4,5. All right, so I'm going to plot each one. Point P is 1, 1. So I'm going to estimate this to be 1. And the other one again is 4, 5. I'll plot a point here, and then 2, 3, 4, 2, 3, 4, 5. That would be over here. All right, so this is a line segment going from P to Q. All right, that's not a vector, that's just a line segment. Now, if I want a vector that corresponds with that line segment, it needs to be pinned at 0, 0. Right, so essentially what I'm doing is I'm taking all of this stuff and shifting it down so that P is at 0. Right, and you can see it throws my whole scale out of whack. Right, but we can find relative positioning, and that'll help us determine the vector. So what's happening, we think about a vector as a movement from one point to another, at least in terms of the plotting of a vector. That's absolutely not what the definition is. The definition, again, is a quantity with both magnitude and direction. And we'll get to examples of that as we go. But what I want to do is I want to get this point to the origin. So what I'd have to do is move that point P 1 unit to the left and 1 unit down. All right. Now, since this is a fixed line segment, that movement going from 1, 1 to 0, 0 is going to change the length of the line segment, unless we do the same movement with Q, 1 to the left and 1 down. All right, so move each point. One left and 1 down. Now that's not all the time. It's only the case that it's 1 left and 1 down because that's how far P is away from the origin. Now I could have gone 1 down, then 1 left. It didn't really matter as long as I took into account the vertical and horizontal movements. All right. So then I would ask myself, because obviously this point is now located at 0, I'd want to know what this point is. So, you know, my scale is a little out of whack, but I did reduce my X value by 1 unit. And I did reduce my Y value also by 1 unit. Let me just kind of clean up the scaling here. All right, so I reduced my Y value by 1 unit also. So that made the new X value 3 and the new Y value is 4. So if I want to create the graph, I need to start off at 0, go out 1, 2, 3 units in the X, and 1, 2, 3, 4 units in the Y. Draw a ray going from the origin to that point and throw an arrowhead on it, and that's vector PQ. So we do, for vector notation, we do kind of like a half arrow. All right, you can do a full arrow if you want. Nobody's going to lose any sleep over that. But PQ is now vector 3, 4. All right, and that's what this notation is saying over here. All right, so this is vector notation, represents the endpoints of a vector. All right, now the magnitude, and we'll get this in more detail later on. The magnitude is just the length of that vector. All right, so you actually come back to right triangle trig, and that's one of the reasons why people kind of find this a little bit more appealing than law of sines and cosines. And it's because you could do everything with right triangle trig. You don't need the law of sines or cosines. But you know, the trade-off is you have to learn about vectors. All right, so it's kind of like, that's what I was mentioning last class, where you start off talking a lot of trig and then you go away from it for a while. but the whole point is so that we could bring the trig back later on with new skills under our belt, right? We call this the component form of a vector. So that's the notation down here. All right, so if you have an initial point and a terminal point, x, y, it doesn't matter what the subscripts are. You have two distinct points. What you're going to do is you're going to subtract from your initial point. You're going to subtract the second point. You could go either way. Actually, it doesn't really make a difference. So I'll just show you real quick. So if I did the computation for this problem here, because I know I have another example, but it's nice to kind of pay it off here. So if I'm looking for PQ, oh, I think sorry, I misspoke. It does matter which way you do it. I'll explain that in more detail in a sec. But we're going to take the second value and subtract from it the first value. So 4 minus 1, and then 5 minus 1. Right, so that would give you the 3, 4. We look at, we use the subscripts of I and T. Some people use I and F for final. We say initial and terminal. Right, so that's why it gets a subscript. So this would be the initial point. And this would be the, well, I actually have it labeled there. Shocking. So this is my initial point, and this is my terminal point, and that's why they get subtracted in the order that they do. All right, terminal minus initial to figure out the component form of a vector. All right, I misspoke earlier when I said that it didn't matter what order you subtracted it in the sense that vectors have magnitude and direction. You need to do terminal minus initial in order to get the direction part of it. But in terms of the magnitude, it doesn't matter what order you subtract it in, because whether it's pointing to the upper right or lower left, or upper left or lower right, it's the distance that matters. And so we obtain the absolute distance from the end point to the terminal point to the initial point, and vice versa. So the length of the line segment doesn't make a difference. If I go this way or if I go that way, that length is still going to be the same. All right. So that was what was rattling around in my brain when I made that comment a few minutes ago, but hopefully that shed some light on it. All right. So just another example real quick, because you see all these operations below, and the notation can be kind of intimidating. So let's get another one under our belt first. This is our initial point. So this is my X sub I, Y sub I, just using this notation now, and X sub T, Y sub T. All right. So the vector, and you call the vector whatever you want. Typically, when we have unnamed points, in the previous one, it was point P to point Q. So we just call it naturally vector PQ. All right. But sometimes they just give you the points. In that case, we just go with V for vector. And if you have more than one pair of coordinates, then you start naming your vector with the letter V. And then if you have another vector, you call that, you could do one of two things. You can call them with subscripts, V1, V2, V3, or you could start working your way down the alphabet. But you realize you run out of alphabet pretty quickly. So V and W are pretty typical names for vectors. But as you go forward, I say the same thing over and over again. I don't know what you're doing after this class. If it's going to be calculus, you might find yourself in a linear algebra course where pretty much all they use is subscripts. Right. So it would be vector 1 is V sub 1, vector 2 is V sub 2, and so on. Right. So subscripts are not a bad idea if you have multiple vectors. Okay. So in this case, again, it's this formula here. So 1 minus -2. Feel free to just make that a plus. And 2 minus -2. All right. The triangular brackets there. Again, that's the notation. That's how we represent that the coordinates that we're stating are the endpoints of a vector. So 1 minus -2, 1 plus 2 is 3. 2 minus -2, 2 plus 2 is equal to 4. All right. So you can see here that you have two completely different coordinates, sets of coordinates, and yet they still give the same vector in component form. All right. So that's something to be mindful of. You could have more than one segment that has the same magnitude and the same direction. In fact, if I plotted this, the original set of points, -2, 2, just kind of rough it in here. What's the other one before I go too crazy? Yeah, so -2, -2. So 1, 2, 1, 2. You have a point here. Now this is the initial point, so this is the one that has to get to the origin. I have also the coordinate 1, 2. That'd be right here. So what I'm essentially doing is I'm taking this line segment and moving it, and I'll just duplicate it. Copy, paste. I'm taking this line segment and moving it up so that it's pinned at the origin. Let me go with a red here. All right, so it's whatever transformation makes that happen, that's what your vector is going to be named. So in order to get where I needed to go, I had to increase the terminal point by 2 and increase the, well, terminal point X and Y each by 2. Right, so 1 became 3, 2 became 4. Right, but essentially it's the same thing. So V, vector V is equal to 3, 4. And also bear in mind, I'm calling this vector V. I'm not just talking about the endpoint, the whole thing. This, I'll go with the green for now. This entire little segment that it's called array, that's vector V. All right, the whole thing, because in order to have magnitude and direction, it needs to create an angle. Right, so that's the direction that we get. Right, so that's a little teaser for the connection with the unit circle. All right, so you have an angle theta, and then you also have a length. That length represents the magnitude. Right. You could also operate on vectors. You can add them together, subtract them from each other, and multiply them. And this is kind of an extension of some transformation concepts where you can shift a vector over to left, right, up, down, sometimes left and up, left and down, right and up, right and down. You could also dilate it. You can double the length, triple the length, whatever. And that goes into these formulas. So the first two, I kind of refer to them in my mind anyway as common sense formulas, right? And what I mean by that is, like, you know, because for some of us, you know, there's nothing about math that's common sense. Right? That's me for that, or was me for certain topics back when I was going through the system. But I would say, I would amend that to say that what we're going to do is probably what you would think to do if I didn't give you any instruction whatsoever. Right? When I say M plus P, well, here's M. Here's P. I'm going to add them together. So when I add two vectors, I add the X components and I add the Y components. So that'll give me a 4 and a -4. All right. Whenever you add, and I mean that in the most general sense, like 2 plus 2, what you're doing is you're transforming the first number by the second number. All right, so the rule of transformation is dependent on whatever the second number is. So for example, if I say again 2 plus 2, well, let me do 2 plus 3. All right, what we're doing is we're looking at these as two isolated things. This 3 is the rule of transformation for 2. I'll say of the 2. All right, so in this context, I'm transforming the 2 by moving it to the right 3 units, right? So it's a rightward shift, assuming that our one dimension is the horizontal axis. It could be a vertical axis. But if I have a 0 here, a 1 and a 2, so this is the point of interest, 3, 4, 5. The rule is that I'm transforming the 2 and moving it to the 5. And that's a horizontal translation, or it's just a translation of 2 units. All right, so in this context, so when for m, vector m plus p, p is the rule of transformation for m. All right, that's the, or you could say encoded in P are the instructions for how to move M. You could also say P is the recipe for moving M. All right, so it's telling us go 1 left and 3 up. All right, and that's because we're working in the plane. That XY plane defines the X coordinate as a horizontal location or movement, and the Y value is a vertical location or movement. And also, M itself could be thought of as a rule of transformation for 0, right? Because there's an implied 0 in front of this. And not to make it too complicated, because it's like, how could you make just adding 2 numbers as complicated as this? This actually helps understanding some of the more advanced concepts down the line. So it's not, unfortunately, it's not me just going on a side tangent and trying to impart wisdom. It's partly that, I guess, but it's it'll be applied down the line. Right. So for example, just tuck it in over here. If I have vector m, this is the same as 0 plus m. Okay, 0 in a 2-dimensional system is the vector 0, 0. Right. So in 2D, which suggests that there's going to be 3D down the line and 4D, less able to visualize things the higher we go in dimension. And that's one of the reasons why we kind of beat the second dimension to death, because if you understand everything about 2-dimensional mathematics, whether it's algebraic, visual, logical, whatever, then you'll understand the higher planes, because I'm sorry, higher orders of dimensionality. So in 2D, that 0 is now thought of, I gotta get a fresh color in here. That 0 is vector 0, 0. So when I add vector m to that, now another way to represent a vector in component form is by using subscripts. So you could say, call it m1, m2. Right, the first component and the second component, and sometimes we do that. Like in this case here, it would be m1, m2. In this case, it'd be N1, N2 as the names of the vector. One of the reasons why we do that is because when we do get to the higher dimensions, well, it goes back to what I was saying before in terms of naming your vectors. Sometimes you just run out of letters. So you start using subscripts, right? So that's another way of doing it. The last one would be P1, P2, if you were wondering. But M1, M2 is the recipe or is the rule of transformation for the zero vector, right? So M1, M2 is the rule of transformation for the zero vector. I'll clean this up in a sec. When I find myself doing all these side examples, kind of run out of road real quick. All right. So a couple of side examples. One is the most basic one, and that is just simple addition. Thinking of it as a rule of transformation, right? The second one that I did down here is specific to this problem. And the last one is just talking about how just any statement of a vector could be thought of as a transformation away from the zero vector, right? So let me kind of partition these off a little bit. So this was one of them. This is my first example. Got a little right trapezoid there. I want to fix that. But anyway, like I said, at this point, it might just seem like it's me overcomplicating the concept of addition, but you'll get to a point, hopefully, where you see that that's not the case. It's one of the reasons why I have a love-hate relationship with this course, because it's the sad realization that a great number of people are not going to see the nice payoffs of this material. Like, why is it useful? Like why do we learn this? Why did you go off on this 20-minute tangent about transformations? I mean, it has meaning. It's just you got to get there. Okay? And if anything, maybe it serves as motivation for some people who might not have considered continuing with math. Maybe you have an aptitude for it, but you're like, I only have to take Calc 1, so I'll be done with it after that. You know, you could take the additional math courses as electives, you know, but you could also, or you might also find out down the line that a course that you didn't think would be required for your major actually is, right? If you're anywhere in the sciences, you got a little bit of a calc road ahead of you. But if you're in the humanities, you might be done at this point. I see a question out there.
Yes, Professor. So actually, I just realized this semester that I have to take calc, and I'm like graduating this semester. So I have to take it in the summer. But I saw the schedule for the summer. Oh my God. It's too tight.
Yeah, I mean, they have the 2 summer sessions,
Mhm.
each are 5 weeks apiece, but they do have a 10-week session that spans from session 1 to 2. So that's as close as you're going to get to like a full semester course over the summer. So at least
Sorry. What do you think about the asynchronous class? Is that possible? Like, is it possible to learn anything, or?
like a lot of other things, it depends on the person. You know, 'cause, I've been in environments where I've done asynchronous, like all the calculus classes. I've done statistics and things like that, and I get such a mixture of individuals. Some who just rely on Google to get the answers, and some who really work to understand it because they know that they need it in the future. So it really depends on what you're planning on putting into the course, really. And you know, some people, they've said it, that like, because I teach in-person class this semester, and one of the things that they said is, if I go to a physical classroom, I'm on the hook for that period of time for just math. I don't have to worry about getting distracted by everything that happens at home and things like that, losing track of things and falling behind. In terms of absorption of the content, like if you do like one of the 5-week courses or even the 3-week course, the one that they have in August, you got to make sure you put aside a good amount of time at home to work through the course material, because it's not, it's not paced by the teacher. Not always. I mean, they'll pace the course for you based off of what they think, but ultimately when the test is scheduled, you got to be up to snuff on the material. So I don't think I answered your question, but
So they do have a 3-week in August?
They do in August. They have a 3-week session. So there's the May to June, end of May through June. That's session 1. Session 2 starts end of June, beginning of August, ends at the end of August. Maybe I'm sorry, skipping a month. End of June to the end of July would be the second session, and the third session would be usually the second week of August through the end of the third week or something like that. And then throughout all of that, they have a 10-week, I don't even think they give it a name other than to say the 10-week session that you can, like, if they offer, let's say Calc 1, that would be over 10 weeks, but usually that's like a synchronous course. Okay, so it could be in person, could be on campus, I'm not sure. Right, so just be on the lookout for those. The 3-week, I mean, if you're looking to bang it out and be done with it, and you have a block of time in August where you're like, okay, I can dedicate it to this course, then that would be a good approach to take. So
Okay, Professor. Thank you.
no problem. So the next one has multiple rules of transformation. So we're transforming vector m first by a scalar factor of 2. All right, whenever you have a coefficient, that's a scale factor. All right, so what we're doing is we're taking m 5, -7, and scaling it up by a factor of 2. All right, so that, again, it's like what I said before, it's what you think it is, just multiply each part by 2. Okay, so that becomes 10 -14. All right, this is also known as a dilation factor, but the scale factor seems to make more sense, because if you're, or the term anyway, if you're scaling something, usually you're going the other way, where, like if you create a scale model of something, everything is in proportion with what you're going to build, just maybe like 1/100th of the size, or 1/8 the size, depending on what it is that you're constructing. All right, so if you create a scale model of a house, then every measurement in the house that you look to build, the scale model should be one whatever of that length. So maybe 1/1000th, but every single one of them by the same measure. All right, so we have a scale factor of 3 for n. So this is plus 3 times n is 0.4. So that's plus 0.12. All right, so I tripled the length of 0, still 0. I tripled the height or width, depending on your perspective, and that became a 12. Now this negative sign here serves multiple purposes, right? Because we can look at this as a scale factor of -1, right? But that negative also has an impact. A negative scale factor or negative coefficient leads to a reflection, right? So, and I'll show you real quick. I have a -1, so -1 vector p -1, 3. When I distribute it through, I'm really taking this whole -1 and bringing it in. All right, so that's going to become a +1, -3. All right, so I've used the negative, so it reverts back to positive. So this -1 leads to a reflection through the origin. Origin. All right, reflection through the origin. All right, so just a quick sketch of that. I have originally -1, 3. Now I have 1, -3. All right, so find the distance from that first point to the origin and just do the same thing, but in the opposite direction. All right, so it should be symmetric over the origin. And then after that, it's, like to talk about every transformation that's going on in every problem, that's kind of not practical. So I have, like I can just say it, I'm not going to write it all though. If I have a scale factor of 2, I'm scaling up 5, -7 by a multiple of 2. All right. I'm scaling up 0.4 by a factor of 3. All right. For the last one, I'm scaling vector P, -1, 3 by a factor of 1. So no change, but I'm also reflecting it through the origin. All right. So then when I look at these two together, 10 plus 0 is 10, -14 plus 12 is -2. I have now translated vector 10, -14 up 12 units because there was no change horizontally. All right, so I'm shifting. It's a matter of motion. I'm taking points, I'm sliding them in one direction, flipping them over an axis, however you want to think of it, but that's essentially what's happening. Now, 1, -3 serves as the transformation rule for 10, -2 by telling us to take that 10 and shift it 1 unit to the right, take that -2 and shift it 3 units down. All right, so all of that is really just kind of a discussion of what kind of transformations are happening, but ultimately the computation is fairly straightforward. All right. Kind of bouncing around. Origin. Yeah, I wasn't sure what word I was going to make the second word of the day. Origin, as in coordinate 0, 0, the origin. Right? The intersection of the X and Y axis, also known as the origin. All right. So one last thing before we call it a night. The visual representation of vector addition, vector, subtraction, scalar multiples, scale factors, things like that, right? Because there's a way to do it that doesn't involve any kind of computation. Sometimes you just want to have a sense of where the new vector would be or what its relationship would be with the original vectors, but you don't want to actually do the math, right? And in other cases, it's just kind of a way to get a sense of what the physical attributes are after you do a computation. So if I can easily do this computation, U plus V is going to be 6, 4. All right, what did I do? I added this number to this number and got that number, added this number to this number and got this number. All right, but we want to be able to do it graphically. And, like I said before, when I was doing the law of sines, cosines problems, if you have an app with a stylus of some kind, this becomes a lot easier because what I'm going to do involves like physically moving line segments. Right, so unless you want to measure the angle and length of each one,
you know, the app becomes a better way to do it, but I know it's not practical for everyone. And so if I want U plus V, again, V is the transformation rule for U. All right. So what I would do is I would take this length and slide it on over to the very tip of vector U. And that would create a new point. All right, so I'm taking this line segment and just sliding it on up so that its tail is at the tip of the other vector. But we call the tail to tip method. All right, there's also a parallelogram method, but it's, you know, like if you know one, you don't really have to worry about the other. All right, so again, I'm just taking this line segment, same length, same orientation, and sliding it up so its tail is at the tip of the other vector. All right, then what I'm going to do is connect the origin to that new coordinate. This red vector, I'm going to put an arrowhead on it. This red line segment, now a vector, is U plus V. All right, so that's my vector U plus V. Sometimes they say let W equal U plus V, plot W. All right, but this is a nice, straightforward approach for finding the sum of two vectors. All right, so and you know, like this is the kind of question I always put on the test: graphically find the sum of the two vectors. And unfortunately, what people do is they'll, okay, forget about this. All right, I know the sum is 6 plus 6 comma 4, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I went by half units. So I'd have to go, so 4, 5, 6 would be over here. And then 1, 2, 3, 4, I went by whole number units here. And they'd say, okay, well, I'll just plot that there and then just draw a line segment. Oh, messed that up. All right, and for the record, this is not the way to do it graphically. Even though it'll get you the same location, it's not a graphical approach. All right, so you see it's pretty much the same. All right. We don't want to do that. In fact, I don't even, when I ask a question like this, I don't even care if you give me the number, the ordered pair that represents the vector sum. I just care that you can draw the diagram correctly. All right, so I'll do the next example. And so this would be our complete answer here. All right, so we're kind of looking at it in a symbolic form. All right, it's weird. I don't know why I have the same graph twice. I don't know. So this shouldn't be here. Maybe I wanted to show two different ways to do it. I forget. Oh, well, I might as well show you the other way. The other way is kind of, it's overkill. So this is tail to tip. The other way is the parallelogram method. So what we do, we start off pretty much doing it the same way, and you'll see why it's overkill. So I take this line segment and put it up here. Take this line segment and put it over here. So I have two tail to tips going on. The intersection here, that would be, we call it the resultant vector, but we also call it the vector sum. All right, so this would also be U plus V. So like I said, it's overkill because you look at the difference between my first diagram and my second one. It's the same, except I didn't draw this line segment, but I didn't really need it.
All right, so this is the parallelogram method. Parallelogram. Gram method.
All right, which is really not adding anything to the conversation. The thing that specifically math teachers kind of like about the parallelogram method is that you could use your triangle, your knowledge of triangles to solve for missing sides and angles and things like that. So it incorporates more of like law of sines and cosines. But the whole point behind me showing you the stuff about vectors is so that you can sort of have an alternative to the law of sines and cosines. If we do it this way, then we're still going to need to use law of sines and cosines to find that missing side. If I needed to know the magnitude of this line segment, I would need to know the length of that side, which I would require law of sines and cosines because there's no right triangles there. Right? Tail to tip just gives us the diagram, but then we could use Pythagorean relationships from there. Right. The next example, 3W. All right. So what I'm going to do is I'm just going to draw a coordinate axis here. All right. So just kind of do it in this space. Note to self, create a better space for me to do this. I'm not going to put the arrows on. So I'm going to take W, its size and orientation preserved.
Hmm.
And I'm going to pin it at the origin. So that's now W. Then V, same deal. Pin it at the origin. So the first thing that they were asking me to do is find 3W. All right. So everything about the position of W is going to get tripled. All right. So at any point along this line segment is going to get tripled. Now it's positive X, negative Y. If I multiply positive X, negative Y by 3, it's not going to change the sign. It's still going to be positive then negative. So what I'm going to do is actually triple it, but visually, not computationally, because I don't know what the coordinates would be for W. All right. So I'm going to take 2 more of these line segments and tack it on at the end. Preserves the size and the orientation of the original line segment, but putting it together, it triples the overall length. So that's W. I'm going to use a more poppy color here. This new line segment becoming a ray, that would now be 3W. Then V plus W, that goes back to the original stuff. So, sometimes what people like to do is do them on separate graphs, just so it doesn't get cluttered. But I think this one's okay, because all I'm going to do is apply the tail to tip method, and I can apply it because addition is commutative. I could treat W as a transformation rule for V, or I can treat V as a transformation rule for W. It doesn't make a difference. All right. So I'm going to take my V and put its tail on the tip of W. All right. The new line segment coming from the origin to that new point. This new line segment creating a new vector, that's the vector sum V plus W. It's actually technically W plus V, but again, addition is commutative, so it doesn't matter. All right. And then the last one, it's got all the trimmings. It's saying double the V. All right, so double the length of V, then subtract from it W. All right. The subtraction part is a little strange, but I'll show you that. So first, I'm going to start off with doubling the V. So I'm going to take the length of V.
and double it. Same direction though, extend the direction. All right, give it a new color. Gonna go like this purple here. This whole line segment is now 2V, or the new vector, I should say. All right. Now 2V, that was the easy part. The other part, the negative W, we can think of this as 2V plus negative W. All right, so all that's telling me to do is, starting off at the origin, take my W and just go the other way with it. All right, so let me just move this for a second here. This is my line segment W, copy. Paste it up here. Make it a different color. So the darker blue there. All right, so this new line segment here is my negative W. I already forgot which color I used. Negative W. Creating the vector. Again, same deal, negative W. All right, so what I want is the sum of 2V and negative W. All right, so I just got to sort of ignore everything else that's happened here and just focus on this vector and this vector. We'll use the tail to tip method to figure out the resultant. All right, and so what we would do is take this line segment, slide it on over here. Its tail goes on the tip of 2V. And then I'll have, if I go from the origin to this new point, get an orange in there. This new line segment creating a new vector would be 2V minus W. All right. So that was like out of the frying pan into the fire kind of deal. Like it went from, oh, I just moved this to that, to, whoa, what just happened? So what I'll do is next class, I'll start off with another example along these lines, just so we can kind of get another look at it. And I have some extra practice that I'll be posting in the extra practice link on Brightspace. Right. So there, I posted some stuff last week for law of sines and cosines. So you need practice with that, it's there. And I'll get some more stuff related to this up there, because I know this is kind of a whirlwind. And it's like, all we're doing is adding in the most complicated fashion ever. All we're doing is creating new line segments in the most complicated fashion ever. So I'll see if I can uncomplicate that for you within the next couple of days. Okay, so I am going to stop the recording.